Hello everyone. In the past few lectures, you have already seen that how we can invoke different kind of constructs in programming and how we use them to write efficient programs, good programs in C. However, one of the fundamental concepts that we have not introduced yet is that how we represent the data or the numbers in such kind of a computing environment. This is very essential because programming is all about accessing the data from the memory and processing it in terms of your computational capabilities and thereby producing the desired outcome that you wish. So one of its parts that we didn't look till now is how such kind of data being represented in the memory. That is, the traditional number systems, as we know that actually we are conversant with decimal number systems, but computers usually listen to binary number systems and they store data in terms of binary numbers or bits. Now, this is very important because since computer has a finite memory size to operate with, you cannot go on storing arbitrarily large numbers in the computer memory. Specifically, you cannot store going on and storing recurring fractions in computer memory. Somewhere you need to truncate and you need to approximate. And therefore, we need to exactly know what kind of representation in the bottom line goes into the memory, how we access data and when do we add, subtract, this kind of operation. Actually, in the device level, what happens? Because this might help us to know some of the errors or some of the mismatches in the data that we get. We divide this lecture into two parts. One part will be to start with the number systems and representations. Primarily the integer numbers with a little bit of hint on the fractional number. And we dedicated a separate lecture on the floating point representation, which is very essential since it has a diverse nature of an arbitrariness, so that we need to succinctly monitor that separately. Today's lecture is going to be of number systems, its elementary representations. There is the binary particularly catering to the binary numbers which are actually done in the computing memory. So first of all, we are all conversant with decimal number systems. It has a base or radix we call 10. That's why we have 10 digits 0 to 9. And it's a positional number system because the position of the digit is multiplied with 10 to the power some factors depending on its position. So the digit position starts from the right to left as 0, 1, 2 and so on. So the value of a particular number string is the most significant digit into 10 to the power that position number plus and summing up with the least significant digit into 10 to the power 0. As here, it is 234 is represented as 2 into 10 square plus 3 into 10 to the power 1 plus 4 to the power 0. And after point, what we do, we go on doing 10 to the power minus 1. And here, before point, we start from right to and traverse towards left. That is 0 into 10 to the power 0, 5 into 10 to the power 1, 2 into 10 square. Whereas after point, we go into 10 to the power minus 1 into 6, 10 to the power minus 2 into 7. That is from left to right after point we traverse. This is how we get out the number in following convention. So since computer uses binary convention, so we need to know how binary numbers are represented, how it is stored. So as you have already familiar with binaries, it has two digits 0 and 1. So it has radix 2. Therefore, when you try to compute any decimal equivalent of a binary number, the same philosophy we follow. That is, we start from right and go towards left. The rightmost position value, that is 0 into 2 to the power 0. Earlier it was 0 into 10 to the power 0. Since it's a binary system having a base or radix of 2. So 0 into 2 to the power 0 is the decimal equivalent that contributes from this position. Plus 1 into 2 to the power 1 plus 1 into 2 to the power 2. So this is basically 4 plus 2, 6 plus 0, that is 6. So this number is decimally, in decimal, we have the value of this number as 6. For fractions, since we started from going from left to right with a 10 to the power minus 1 in decimal, here the base is 2. So we will go 0 into 2 to the power minus 1 plus 1 into 2 square. In this way, the left the left part before fraction will traverse from right to left. So we split in terms of the fraction with the powers. The left part we traverse from right to left as 10 to the power 0, 10 to the power 1 and 10 to square, such as multiplying this way. So in binary we go 2 to the power 0, 2 to the power 1, 2 square in this way. And the right side part we go in decimal from the left to right as 10 to the power minus 1, 10 to the power minus 2. In binary we go as 2 to the power minus 1, 2 to the power minus 2 in this way. So therefore this number in decimal is 5, the integer part, and the fractional part is 0 into half plus 1 into 1/4, that is 5.25 is the number. So all these are positional number systems as we already introduced, because each position has a significance, and from that position we could compute the values of the overall number in decimal. So in binary, since there are 10 symbols, radix is 10. In decimal, and in binary there are 2 symbols, so the radix is 2. You can have variants of such kind of number representations in octal, that is we terminate at a radix 8, so we have decimals from 0 to 7, 8 symbols. Hexadecimal numbers, there are 16 symbols to represent a particular digit, so the base is 16. But the philosophy is same. Before point, you go from right to left, 16 to the power 0 into f, so f means 15, so that is 16 to the power 0 into 15. 16 to the power 0 into a, so a means 10, because 0, 1, 2, 3, 4 up to 9, a is 10, b is 11, c is 12, d is 13, e is 14 and f is 15. So the left part is this way, and the right part 3 into 16 to the power minus 1, that is 3 by 16, plus 12 into 16 to the power minus 2, that is 12 by 16 square in this way, this side. So the philosophy of making any positional number to decimal number is the same, and but there are different strategies that we will see next to convert decimal numbers into these forms. So we start with one by one. Let us first try to see how we can convert binary to decimal. I will introduce you the process, and I expect that as homework you will try to write the C programming code of the same. That is, you write a function which takes a binary number as input, and the function returns a decimal number as output. So the process is very simple. That see, a binary number, first of all, let's say binary number, before fraction if there are n digits and after fraction if there are m digits, then the binary equivalent of this is nothing but you go with I from minus m to n minus 1, your digit into 2 to the power I. Because see, b, this position, that is b minus 1, this position is b1 into 2 to the power minus 1. This position is b2, b minus 2 into 2 to the power minus 2. This position decimal equivalent is b minus m into 2 to the power minus m. Therefore, the corresponding value of decimal is, you have to sum this up, the whole positional values, into 2 to the power of ith index of that position, and then you will get the values in decimal. So I request you to write a simple iterative version of this program, and secondly, can you write a recursive version of the same? For example, if you see this, that if there is a binary number, we just convert it in this way, 43. This we convert it 3125. So you just can work out by your hand. So 101.11 is 1 into 2 square, 0 into 2 to the power 1, 1 into 2 to the power 0, plus 1 into 2 to the power minus 1, plus 1 into 2 to the power minus 2. So this is how we convert binary to decimal. Pretty simple. Now the reverse thing. How do we convert a decimal number into binary? So first of all, let us look at the integer part. Suppose the decimal number is given to you as integer. The integer part, how do we convert? So what we do is that we try to divide the number by 2 and also try to see what is the remainder. So 89 divided by 2 gives me remainder 1, and the result is 44. We go on. 44 divided by 2 gives me remainder 0, result is 22. 22 by 2, 11, remainder 0. 11 by 2, 5, remainder 1. So in this process we go on until we hit upon that the number becomes 0. And it will indeed be the case, because since you are performing integer division with respect to the 2, therefore somewhere down the line you will hit upon a 0 just after you get a 1. So 1 by 2 is 0. So then you traverse from lowest part to the highest part of the remainder values, that is 1, 0, 1, 1, 0, 0, 1. So that is your binary equivalent. Now, just you can think, and it's a very simple algebraic calculation, that why such a process results you a binary equivalent like this. You can just algebraically take a number and can take its bit position as B1, B2 as I have shown in the earlier slide, and can formally prove that this process will indeed result the binary equivalent of this decimal number. Let us take another example. 66, 33, remainder 0, 33 divided by 2, 16, remainder 1. From 16, whatever you divide, your remainder will be 0 until you get a 1, you divide by 2, you have result as 0 and your remainder is 1. So the number is 1, 4 zeros, then a single 1 and a 0. That is your 66. Similarly, 239, just verify yourself. So it will be this way. You do it in your own and verify whether the result comes the same or not. Now, having known this procedure, I would request you to write a iterative function and a recursive function for the same. So, see, now the flavor of recursive says that the last computed function is first to get the result. See, we are dividing and getting the remainders and then printing it bottom up. So, therefore, the last remainder is printed first. That is, you can efficiently write a recursive program to do this, because you know that the function call goes on and the last function call returns first. So, the last function call may return and the last remainder. In this way, if you think and write, it will be very easy to write. So, this is just the integer part of the decimal number converted into binary. Let us see how does the fractional part gets converted. So, suppose we have a number which is 0.634. What we do? We multiply by 2. So, 0.634 into 2 becomes 1.268. We get a 1 as an integer part. We keep that 1. And the rest of the fraction part we take again and multiply by 2. It becomes 0.536. We take the 0. Then the rest part again 0.536 into 2, 1.072. So, whatever be in the integer part after multiplying by 2 at each step, we keep on writing it. Here is a very interesting observation. I request you to listen very carefully. Now, see the number 0.634, if you try to convert it into a binary equivalent, it may not get a finite length binary number. It may iterate over and over infinite times. So, there are numbers which in finite sized space you cannot fit in. So now think of the perspective of a computer memory, that suppose you want to store this 0.634 in the memory. Since your memory is finite, you cannot store by going on doing this. So in the next lecture, you will see that there are representations in floating point numbers. We call such numbers as floating point, you know that. So such floating point numbers are represented in such a way that we could keep only a fixed size depth for them. And that is why sometimes you will see, even if you have declared a floating point number, say 2.5. So you just declare in your program float n equal to 2.5 and try to print n, or maybe after some operations you try to print n. You declare floating point number f n equal to 0.634 and try to print it. You will see that it will not be exactly 0.634 returning. It is either return 634000001 or 633999. Why that is the case? Because depending on a finite representation of the memory, it could not store 634 wholly. Somewhere it need to approximate by cutting it down to a restricted number of bits. And that is where it tries to approximate either 634001 or 633999, not the exact 634. That is the reason sometimes when you try to print some floating point numbers from your computation in C, you will figure out this kind of discrepancies between your number and the result. This is precisely due to the representation in the memory that is finite. However, if you look at another example, that is 0.625, you will see that it is not going to recur again and infinite times, because if you multiply 4 times, it will eventually go back to 1 and your fractional part will be 0. So we will stop here and tell that this number is 0001 after point. And this is indeed the case, because first 0 is half, second 0 is plus again 1/4, this is 1/8 and this is 1/16, and I know 1/16 is 0.6025. So that is why some numbers, in this case, if you declare this number as 0.625, even if the example that I told that 2.5 has a finite length to express, so 2.5 you may not get as an answer as 2.4999, but in 634 there is a chance that you get an answer not equal to 0.634, even if you expect that, because of the finite length memory cannot store this infinite sequence. Similarly, you can also explore that 37.635. So 37 we have done in the decimal part, we have done it, the integer part we have done it using division and taking the reminders and then writing them bottom up. The fractional part we will multiply, put the integer number here and move on until we reach a 1. So 37.0625 is nothing but 100101. In the previous slide we got it, and in this slide we got 0.0001. Okay. So your job is to write 2 programs to convert decimal to binary and binary to decimal, both in iterative as well as in recursive form. I hope you will enjoy writing that. Let us move on. As we have also discussed some other positional number systems such as hexadecimal number, which has 16 different symbols. And you can see that 16 different symbols, 0 to 16, the binary representation of that is a 4-bit representation. Each of the symbol is a bit. We call it as a bit. So from 0 to F, we have this binary. So 0 is all 0. Then last is 1, 1, 0, 1, 1, 1, 0, 0. So I go on like this. Hence, it is very easy to convert from a binary to hexadecimal and vice versa. Because since I know that there is an equivalence of 1 digit in hexadecimal to 4 simultaneous digits in binary number, so I will group the digits in 4 and try to replace it with an hexadecimal number equivalent. But the only concern you have to make sure is that for the integer part, since you are traversing from right to left, you have to append leading zeros if necessary, because it may so happen that your integer part, let's say, have 6 bits. Now if it has 6 bits, so the rightmost 4 bits will lead up to 1 hexadecimal digit. The leftmost 2, if you do not append it with other 2, it will not resemble with any of the hexadecimal digit, because a digit is equivalent to 4 bits. Fractional part, left to right we have to go. Since then, therefore, we have to add trailing zeros if necessary to group it into 4. Now it is adding leading zeros for the integer part and adding the trailing zeros for the fractional part is indeed conceptually also correct, because leading 0 in the integer does not change your number, and trailing 0 after your decimal point or the point position or the fractional part, trailing zeros does not change the number at all. So it is, you are not changing the number, yet you are using it because you want to just directly see how the hexadecimal goes on. Here is an example. So let us go at the 4th example, because the other one is just grouping by 4. Here you see 1 0 cannot be grouped, so it should be prepended with 0 0. So 0 0 1 0 equivalent is 2. See the 4th number. It is, left one is 1 0 1. I need 4 digits, so I prepend with another 0. So 0 1 0 1 is my 5. The right side 0 1 0 1 is 5, and this is 1 1 1. It should be appended with a 0 at the end. So 1 1 1 0, that is your 14, which is E. So this is, and we write it in this way. In the subscript we write 2 for the binary number, in the subscript we write 16 for the hexadecimal numbers. Hexadecimal to binary conversion, just the opposite. If you have understood the binary to hexadecimal, these things are pretty easy. 3A5 is nothing but 3 equivalent to this 4 bits, A equivalent to next 4 bits, 5 equivalent to last 4 bits. 12.3D, this is nothing but 12 is 1, this is 2, point this is 3 and this is D. Pretty simple. You can write an automated program for this also. Now there is a concept you see in C. When you write or declare variable, you have an option to write an unsigned int. It means that it will not use the sign, or in other words, the number is always positive. So with n bits, without sign, an unsigned binary number you can represent from 0 to 2 to the power n minus 1. How 2 to the power n minus 1? Because if all of the bits are 1, that is the maximum number that you can represent, maximum positive number. All of them are 1 means it is 2 to the power 0 plus 2 to the power 1 plus 2 square up to 2 to the power n minus 1, which is 2 to the power n minus 1 if you compute the GP series sum. So now for example n equal to 3, you see there are 8 distinct combinations. 0 to 2 to the power 8 minus 1. So first one is 0 and the last one is 7. So the range of the numbers, when we say we have a 32-bit number, we can express using 32-bit 0 to 2 to the power 32 minus 1. Therefore, if you declared an integer to be an unsigned integer, and if your number of bits that the integers can be stored is of 32 bits, that is 4 bytes, then the maximum number that you could store in an unsigned int is 4294967295. That is 2 to the power 32 minus 1. Now, if it is a 64-bit, if you use, then if your n is 64, then it is 2 to the power 64 minus 1 is the maximum integer that you could represent in an unsigned int in your C language. Now the trivia is that you may try to see, you declared an unsigned int, initialize it with the maximum number, add a 1 to it. What will happen? Just try to check it out. What will happen if you add maximum number plus 1 in the integer? Similarly, have an unsigned int in your code, initialize it with 0, subtract 1, see what happens. Now, this is an unsigned representation. However, in our computer, we have representations which are of signed form, because when we declared int some variable, then obviously that is signed, since we can also write negative and positive values into that variable. So, many numerical data items used in the programs are signed. So, how to represent a sign? There are 3 possible approaches: sign magnitude, 1's complement and 2's complement. We will first go with each of them and see how it varies. Then we will show you what is actually used in our machines nowadays when we write C and operate over it. First of all, the easiest thing to do here is that you keep a bit reserved for sign. So the maximum number here is, since you are using n minus 2 position up to n minus 2 position, that is n minus 1 bits you are using to represent the number, and the leftmost bit is reserved for sign. So 0 if it is positive, sign bit is 1 if the number is negative. So therefore the maximum number here is plus 2 to the power n minus 1 minus 1, and the minimum number that you could represent is minus 2 to the power n minus 1 minus 1. Because if the front bit, that is the sign bit, is 1 and the rest numbers are all 1s, then it is minus 2 to the power n minus 1 minus 1. So there is one problem of such kind of a representation, because see, any representation should be such that it should uniquely have representation style to represent every number. So when we try to design a representation strategy for a number system, we think of two criteria. One, it should represent all possible numbers within its allowable range, since the memory is finite. Second, no two numbers should have the same representation, or no number should have two different representations. However, signed magnitude representation fails in the last category. Here plus 0 is all 0 and minus 0 is also all 0. because I am only representing the number in this n minus 1 bit and the front bit is signed. So whether plus 0 or minus 0, the value becomes same for 0. So we have two different representations of 0. So let us try to think about another way of doing it. So one is that another possibility is we represent the numbers using ones complement. So by ones complement, I would like to mean is that so positive numbers are exactly represented in sign as in sign magnitude form. So the front bit is 0, the rest bit are all ones, are all magnitude of the number. Now negative numbers are represented in ones complement. So ones complement means that every bit of the number, let's say I want to represent minus 4. So I first represent 4. Then I just complement every bit. So I make 1 to 0 and I make 0 to 1. Let us see an example. So for n equal to 4, see this is 0, this is 1 and we can go up to 7 because most significant digit is my sign. Now if I have to represent, let's say minus 5, what I will do, I will make the rightmost 1 to 0, this 0 to 1, this 1 again to 0. And it's a minus 5, so the sign bit will be 1. So therefore you see 1, 0, 1, 0 is minus 5. To find the representation of minus 4, ones complement of 4, that is 1, 0, 1, 1. So this is pretty simple to implement. But how does it help us? It helps us see now that you can subtract using addition, first of all. So when we write addition functions, subtraction functions, in the computer, inside the computer, there exists a circuitry that in the introductory class we mentioned there is an arithmetic logic unit which is responsible to perform such operations in CPU. So that arithmetic logic unit has adder, subtractor, those units. So here if we can represent it in this way, so only addition will suffice, because if I can just represent it in ones complement form, I do not need to subtract anymore. I just will make the thing complement and add it. And it leads to substantial savings in complexity. However, the fundamental problem of two different zeros, representation of 0 becomes here evident. Here also is a problem, because plus 0 is all zeros, minus 0 you just flip 0 to 1, 0 to 1. So the minus of a number is nothing but one's complement of every bit, that is flipping every bit from 0 to 1 or 1 to 0. So all ones are also minus 0. So we reserve the two different representations for the same number. Here also the maximum and the minimum are as same as the sign magnitude one, that is 2 to the power n minus 1 plus minus as you wish. So to eliminate the possibility of this number 0 representation, we moved into another thing which is called 2's complement representation. 2's complement is just like 1's complement, but when you try to represent a negative number, instead of only complementing 0 and 1 and 1 to 0, first you do a 1's complement of the whole number as shown in the earlier slides. Then you just add 1 to the resulting number to get its 2's complement form. For example, here you see, if I want to get minus 2, what I will do, first I will complement each bit. So minus 2 in 1's complement will be 1, 1, 0, 1. So 1, 1, 0, 1 is my minus 2. So if now I add 1 to it, it will be 1, 1, 1, 0. You see here 1, 1, 1, 0 is minus 2. Plus 4 is 0, 1, 0, 0. Minus 4 is 2's complement of 0, 1, 0, 0, which is 1's complement becomes 1, 0, 1, 1 plus 1. So then it becomes 1, 1, 0, 0. How does it help to solve the two different representation for 0? Because now see, your 0 is all zeros that I want to keep. What will be your minus 0 now? Minus 0 is 1's complement would have given you all ones plus 1, which again becomes all 0 because your size to represent is this much. So if minus 0 becomes all ones plus 1, which will overflow the leftmost 1 out of it. So minus 0 and plus 0 will all become zeros since your size is of n, that is fixed size. Here I am showing with n equal to 4. If your size is n, that is fixed. So 2's complement is 1's complement plus 1, which eliminates two different representations of zeros. Now you see, so if you see here, what you will find that, for example, 6 is your 0, this 110 is your 6, and your, when you say that if you write this 4 bits, so the maximum thing you can write in this 4 bits is 2 to the power 4 minus 1. This many numbers in decimal you can represent, first of all. Now the value actually is minus MSB of 2 to the power n minus 1 plus unsigned value of the rest. So here MSB is 0. So minus 0 into 2 to the power n minus 1 is 3. So minus 0 into 2 cube, it is 0, plus 6 is 6. Here MSB is minus 1 into 2 cube, that is minus 8, plus 6 is 2. So see, this makes sense because here whenever we try to do minus 2, what we do is here is that we complement this. So the complementing means you are making this 7 minus 2 plus 1, which is basically 7 minus 2 plus 1 is 6. So therefore 6 and 2 are complement in this set. You see here 2, you see here 6. You will exactly see these are same, only with the sign bit differing, minus 6 and 2. Okay. So here with a simple algebraic computation, you can easily figure out why I was telling about this value is minus MSB to the power n minus 1 plus unsigned. Two examples just show that this may be true, but you need to formally see, have the bit positions, formally try to prove that this is indeed the case. You will easily get it, why I am telling so. Here now the point is that since two representations are not sacrificed for a 0, so I have one more number I can represent. Hence the maximum is the same as in all other previous representations. However, the minimum I can go one more, because now I have minus 0 is now no more needed to be represented. Plus 0 minus 0 same as all zeros. So I can go up to 2 to the power n minus 1. Similarly, subtraction can also be done using addition. Since I can complement easily, I will add them. Because in complementation, just flipping of the bit and addition with 1. So only addition is required. Almost all computers nowadays use 2's complement representations for storing the negative values. We will see that when we, in our program, when we write addition, when we add two numbers, when we subtract two numbers, how such addition and subtraction of numbers take place. So in examples in C, when you write a short int, it is of 16 bits, though it differs from machine to machine. What is the size? There is an operator called size of. If you write size of short int, it will give you exactly the number of bytes, how much is reserved in your computer. So int or long int is 32 bits, long int is of 64 bits typically. I am not saying it can vary from machine to machine. So you can easily see it, as I said, there is an operator called size of. In bracket you write long int and try to print the size of using %d within printf. You will see what is the size of the long int representation in your memory. So adding binary numbers, I hope this is not much to explain, because only thing is that 0 will produce 0, so as 0 and 1. 1 will give 0 with a carry 1. The same thing happens in decimal, right? Also, if I have 5 plus 6, it will give 1 with a carry 1, that is beyond 10. Since it is 2, that is beyond 0 and 1, so it will give a carry. So here you digit by digit you add on. If there is a carry, you push it on. And if there is a carry out also, you just keep 1 bit extra for that. This is the typical fundamentals of adding binary numbers. Now 1's complement, if we need to subtract, so addition is pretty simple in every kind of form that we have shown, sign, magnitude, 1s and 2s. Subtraction, as we are discussing that It is easy to subtract in 1's complement because only addition is required, because how to compute a minus b? First we compute 1's complement of b, say b1. Then it becomes b1 equal to minus b, that is, we know. Now we compute a plus b1. Now what will happen is that, how to deal with a carry? So if we get a carry after addition which is 1, we add that carry back and put the result as a positive number. And finally, otherwise, if the most significant bit is 1, there is no carry or such, then it's in 1's complement form and the result is negative. We will show an example. What is 6 minus 2 in 1's complement form if we carry out? So 1's complement form, I need to make 2. 1's complement of 2 to make it minus 2. So 1's complement of 2 is just flipping the bits of 0010, that will be 1101. I am assuming 4-bit representations. If there are more bit representations, there will be more 1's prepended in the complement, 1's complement of 2. Assuming 4-bit representation, now if I try to add it, you see here, I get a carry 1. And according to my rule, if I get a carry 1, I go on adding it with the result. So it becomes 4. We call it end round carry addition. And the result becomes positive because the most significant bit is positive. Second example, 3 minus 5. Similarly, 5 we need to make 1's complement to get the value minus 5. So in 4-bit representation, the value of 5 becomes 0101. So in 1's complement, it will be 1010. So then if we add, you see the result we get but no carry. So we do not have to add the end carry. So this is my result, and my result I found that most significant bit is 1, indicating that this is a negative number. If we remove the most significant bit and consider actually the magnitude of the number, that is 101, but it is also in 1's complement form. So the actual negative number, if we try to get it, it is 101 if it is in 1's complement form. In true form, the number is 010, that is 2. So the number is minus 2. That is the result. So this is how we perform subtraction in 1's complement. Addition is the same as we have all seen. Now in 2's complement, what do we do? In 1's complement, there is one rule. 2's complement must be there. There must be another rule to do it. So in 2's complement, what we do is that we first compute the 2's complement of B2. 2's complement of B, which is B2. Then we add. Now, two cases can happen if there is a carry 1, if there is no carry. Now, if there is a carry, we ignore the carry and we result as a positive number. If there is a carry 1. If there is otherwise, if there is no carry otherwise, your number is negative and it's also in 2's complement form. Let us see an example. Again 6 minus 2. So minus 2 in 2's complement is 1's complement of 2 plus 1. So 1's complement of 2 is 1101 plus 1, which is 1110. Now I can directly add these two because minus 2 is this one. So when we add, I get 0100 in the actual position with a 1 carry. So I will just ignore this and make this as my result. No need to add here the end round carries as we do in 1's complement. Why this is so? Because 2's complement is one added representation of 1's complement. Now in generic form, if you try to see why this happens, take this number in generic as B1, B2, B3, B4, and this one is also C1, C2, C3, C4. Try to represent in decimal what does this mean as per the value we given, minus MSB into 2 to the power n minus 1 plus unsigned part. Now when you add that, you will get exactly the value. If there is a carry out, you will see that the value is actual and the carry out can be ignored. So algebraically also you can see this and prove it. I have shown you in some example to make you easier to understand. But if you are suspecting about the theoretical correctness of it, you go by algebraically procedure while assuming the number is of m bits or n bits, b1, b2 up to bn, second number c1, c2 up to cn, and do it. You will get the same thing. What is 3 minus 5? Again, minus 5 is 2 in 2's complement is this. So if you add it, you will see that 1, 1, 0, carry 1, 3 ones 1, carry 1, this is 1, and then again this is 1. So there is no carry out first of all. Since there is no carry, the result is negative. And if the result is negative, then it will be like this. The result is negative mostly because the MSB is 1. It may so happen there is no carry, but the result is positive because you add 1 plus 1. So there is no carry. But in subtraction, where you do, the MSB is 1. So this 3110 becomes your 2's complement form of the number. So the 2's complemented form 110 comes from the number 2. So therefore, I get minus 2 as my answer. So this is how we perform subtractions. You can see more examples. If you represent it instead of 4 bits, as to show you easily, we represent it in 4 bits, but actually it could be represented in more bits too. You can see 18 minus 11. So 11, 1's complement this, 2's complement this, add 18 to that. So when you add it, what will happen? You will get this value with a carry 1. Now carry 1 is ignored in 2's complement as we have seen, so the answer is this. Okay, just do it in your notebook if you are feeling that it might, what is the procedure, you will get it. 7 minus 9. So 9 is 1's complement, you get this in 8 bits. 2's complement, you add 1 to it, you get this. Now you add it. So when you add, you have a carry 0 which is ignored, the MSB is 1 and the rest number, if it is in 2's complement, if it is in 2's complement, so if you get the actual number, it will be 0, 0, 0, 0, 0, this one will be 1 and this is 0, so minus 2 is your answer. So 2's complement of minus 2 is this, the result. So this way we perform, actually it is not we, but when you write in your program, when you add, when you subtract from your program, this is how the internal circuitry tries to do it by only one addition unit in a CPU. Within the arithmetic logic unit, there is only one adder which is responsible to do this. Multiple bit it can take and add it. And finally you get this result. However, you might be wondering now, because since there are limited size of the memory size in your computing machine, so what if I add to arbitrarily large numbers, or may subtract, or what if I add to arbitrarily large numbers? It may produce some number which cannot be fit in the set of digits or the set of memory that you have. Suppose your integer is of 32 bits. Now you add two big numbers which cannot be represented in 32 bits. So how does your system can tell you that there is an overflow in that? So when overflow happens, usually from a human sense, how do we sense it? Because when we add two positive numbers but get a negative number as a result, then we think that something wrong has happened. Either our calculation is wrong, but let us put that aside. So let us think that we are calculating correctly. Computer is calculating rather. We can trust more computer than us. So either your result you produce is a negative number is a fallacy, or maybe two negative numbers you are adding, you are getting a result as a positive number. So in both these cases, respectively, we call an overflow or an underflow has occurred. So another equivalent condition is that your carry in and carry out from the most significant bits differ. This is a very strong statement and needs to be proven. Let us see first example, and I always leave the proof to you because you are smarter, you just cleared IIT JEEs. So you can do an algebraic proof very easily. So that's why, let's see that 64 and 4, if I add it, see there, so from a human sense, if we add it, it is 68. In the binary, if you add it, you get a 68. So the two positive numbers being added to produce another positive number. No problem. Okay, that's absolutely no problem. Now my condition that I want to look for, what I told is that if the carry into the MSB and carry out from the MSB differ, then only there is a chance of overflow. Here the carry into the MSB is 0 and carry out from the most significant bit MSB is 0. So it is correct. Whereas 64 plus 96, you see actually this sum is much more than what we can represent maximum in 8 bits. Because the sum of 64 and 96 is how much? 160. But in 8 bits, we can represent up to 127 if all are ones. So 160 we cannot represent. Now in binary, if you try to add, what will happen? You see here it is 1, 1 is 0. Then carry 1 is here. Now this thing is minus 96 because your most significant bit is 1, which gives you a minus number, and the rest number, if you try to think it in 2's complement, the actual number will become 96 because it will become 1, 1, all zeros. So this will become 96. 64 plus 32 is 96. So therefore, you see the two positive, in human sense, you will see two positive numbers giving rise to a negative number is obviously an overflow. But in machine, how did it sense? See, the carry into the most significant digit is 1. This 1 produces a 1. This 1 plus 1 produces a 0 with the carry 1 in the most significant digit. But that one just goes in 1 here, do not produce output as 1. So in this case, I would say that there is a overflow that has happened. So this is how we detect the overflow mechanically. Rather than in a human being, you can know that this number is a negative number. We are adding two positive numbers. So why that human being sense cannot be implemented in the circuitry? It can be implemented. We have to have some additional circuitry for that, because we need to know these two numbers are positive and we need to also sense that these numbers is negative. See, now you have to compare that if this is 0 and 0 and this is 0, this is 1. Then only we can say there is an overflow, there is a comparator involved in it and all that. However, here you see, you just need to see whether the carry in and carry out, these become 0 and 1, differ. These two are not equivalent. And how do we implement the circuitry for difference? ANDing them produces 0 means differing. Exclusive, no, differing. Sorry, ANDing will not always give. See, differing, you can see that exclusive OR produces 1. You just have an exclusive OR gate between those two bits and see if it is 1, then they differ. So the circuitry to check the most significant bit carry in and most significant bit carry out differs is much simpler to implement than the circuitry to humanly detect that two positive numbers giving rise a negative number or two negative number added with giving rise a positive number. So that's why we have this kind of a method. Now, why this is the case, I leave it to you to formally prove. Again, you can use B1, B2 such generic representations and can see why this becomes. Okay, I leave it this to you as an exercise. So, therefore, in this lecture we have studied that numbers are a very essential quantity to represent, because all of the programming is how you can access numbers, represent numbers and perform certain operations. And this is more we need to know this representation, because sometimes the numbers cannot be represented in finite length, as we have seen for the binary equivalent of 0.634. So therefore we need to truncate the number, and hence certain operations we need to perform otherwise, because we cannot exactly represent in finite memory space. And we have also seen there are internal circuitry and there are many interesting ways to avoid certain kind of operations like subtraction by using 1's complement and 2's complement form. 2's complement being prevalent in nowadays machines, that you can just have an adder circuitry to do all the operations and detect when the overflow is happening in your finite memory and underflow is happening. So with that note, in the next lecture, preferably we will try to see how this floating point is represented, how the floating point operation reveals to you. Okay. So I hope you will take this lecture, and the programs that I want you to write, you will write it and have fun. Thanks for your attention.